Hello and welcome to a new class in construction scheduling. And today we're going to talk about network compression. Last time we were talking about project updating, and based on the project updates we might find out that the project was behind schedule or ran a little bit behind schedule. And we know that there's a concept called liquidated damages. However, liquidated damages do not always seem to be a remedy for the project delays, because some projects cannot lend themselves to liquidated damages anyway. Assume, for example, the Olympic Games, the opening ceremony of the Olympic Games. This is an event that's going to be watched by billions of people worldwide. Can a general contractor, for example, responsible for painting the main stadium, say that I'm not ready yet, can you please delay the opening by 1 day or maybe by 1 hour or 5 minutes? That concept does not even exist. Therefore, in some cases we have to compress the duration of the project to take care of the delays in order to finish the project on time. And that's the main topic of what we're going to be discussing today under network compression. So time and money are two major aspects or two major functions in any construction project that the project manager has to master. Construction projects are always have planned and expected finish deadlines assigned by the owner and stipulated in the contract. So the contract is going to tell you, for example, that this project needs to be completed in 200 either calendar days or work days, depending on the clauses in the contract. And what if the contractor does not meet that deadline? So if the contractor cannot meet the deadline, the contractor may need to pay the owner liquidated damages, which are basically assessed on each time unit of delay. In some cases it can be an hour, in some cases it can be a day, in some cases it can even be in minutes. And it's not uncommon for some construction projects that are quite critical to have liquidated damages assessed in the thousands of dollars per minutes of delay, not even hours or days. Depending on the conditions of the contract, the contractor may receive a bonus, on the other hand, if he or she can finish the project ahead of schedule and the owner can start making use of that project on an earlier basis. Some contracts may also include a penalty clause in addition to liquidated damages, or as a substitute for the liquidated damages, it can include a penalty clause for late completion of the project. So the liquidated damage, as we mentioned, is a stipulation in the contract of a monetary amount that must be paid by the contractor if he or she fails to satisfactorily complete the project by the contract finish date. We discussed in a previous discussion the different types of delays, and we mentioned there's an excusable delay where the owner can grant the contractor an extension of time, a compensable delay which is caused by the owner, and in this case the contractor might be receiving some compensation from the owner for any extra losses that the contractor may have incurred, in addition to time extension. There's the non-excusable, non-compensable delay, where the fault or the reason for delay is the contractor's fault. And the fourth type, which is the most complex type, which is the concurrent delays, which is more than one reason occurring at the same time. So a substantial completion is usually accepted to stop the calculations of liquidated damages. A substantial completion basically is the date by which the owner can practically start making use of the project, and is different from the actual completion date. So the contractual final completion date is different from substantial completion, but usually in most of the cases liquidated damages would stop if the project is complete by the substantial completion date, or if substantial completion has occurred. So why does a contractor have to accelerate the project? In case of a non-excusable, non-compensable delay, which is basically the contractor's fault, if the contractor wants to avoid paying liquidated damages, they will have to accelerate the project. So this would be called a contractor-driven acceleration to get rid of a delay caused by the contractor. In some cases, even if the owner has delayed the project, but they still want the project to be completed on time, they would pay the contractor an extra amount to finish the project on time. Therefore, this would be an owner-initiated acceleration to get rid of a delay, whether it was excusable or compensable delay. So the contractor normal finish date is in the baseline schedule. If he does not meet that date, then they will have to accelerate. After starting the project and during project updating, contractor finds that the project is behind schedule. Again, in order to avoid paying liquidated damages, they will have to accelerate. Or if the contractor wants to receive time incentives, if so stated in the contract. The contract says there's going to be a bonus for early completion, even ahead of schedule, so the contractor wants to make use and to benefit from that bonus, therefore they might accelerate the project. Or even if there's no such bonus in the contract, the contractor might know that finishing the project early would allow that same contractor to use the equipment and the other resources on other projects, therefore gaining more jobs. So in this case, they might tend to or want to accelerate the project on their own without a need or without a request from the owner. And finally, if the owner has directed the contractor to accelerate, that would be the owner-initiated acceleration. The question now is how to accelerate the project. Which activities affect the completion of the project? As we have learned earlier, only the critical activities affect the total duration of the project. Non-critical activities do not have an impact on the total duration of the project until they become critical themselves. So to accelerate the project, revisit or study the schedule thoroughly to find any errors or unnecessary logic or constraints. Like, for example, we can change a finish to start activity sequence into a start to start with lag, or we may increase the amount of overlap between the activities, or we may condense or consolidate activities into one activity rather than more. Another option would be to fast track the project by breaking it down into smaller packages and starting the construction of earlier packages while the latter ones are still in design or bidding. So instead of designing the whole project and then bidding it and then building it, we can divide the project into packages, the foundations, for example, or the substructure work as one package, and as soon as it's complete in design, we can start bidding it and we can start building it while the superstructure is still under construction, under design. Change the method of construction or sequence. All of these are different methods to accelerate, using different method of construction, using different equipment, using different material that can accelerate the construction. Conduct value engineering, productivity improvement, and constructability studies. How can we increase the production rate? Because basically, as you remember, the duration is obtained by Q over P, quantity divided by production rate. The quantity is not going to change as long as the scope doesn't change, but if we can change the production rate, that's going to reduce the duration, therefore achieving time compression. We can also work overtime or an additional shift. We can offer incentives to workers or crews for improving productivity. And we can acquire more workers and equipment, basically adding more resources, which is going to be quite costly. Special materials and equipment that can help speed up the work process. For example, in concrete mixes, we can add accelerators that are going to accelerate concrete gaining enough strength so we can move the form work faster and move to a next floor. Improve project management or supervision. Definitely, this is something that a successful project manager can do to improve the quality of work and the speed of work at the same time. And improve communications among parties, particularly during the submittal process, to expedite sending the submittal, reviewing it, approving it, and starting the construction based on that submittal. So, in order to accelerate the schedule, the short story is that the contractor will most likely need additional resources or better utilize existing resources. As a project manager, you should know how and when to accelerate the schedule and understand the trade-off between time and cost. And we're going to talk about different types of costs and their behavior with time. So with the time and cost trade-off, under normal conditions, if the contractor has to work without any pressure from the outside, they're going to develop the schedule, they're going to develop their production rates, they're going to get their durations, and they're going to get a certain completion date for the project. This duration for the activities and this duration of the project is what we call the normal duration, which is the duration with no external pressure. So it's the original duration for each activity, which is the duration it would normally take to complete the activity without any pressure. The cost associated with completing the activity within its normal duration is called the normal cost. So now we have normal duration, and related to that is normal cost. Now, what if we want to reduce that duration, compress that duration? Basically, we're going to use more equipment, more labor, more materials. We're going to change the method of construction. We're going to work overtime. Any of these things are going to reduce the duration of time, but at the same time, they're going to increase the cost. So, in this case, the shortest possible duration to complete the activity is called the crash duration, beyond which you cannot reduce the duration of the activity, which is achieved through the highest possible productivity and maximum, not necessarily optimum, use of resources. We might use resources more than the normal rate. There's going to be probably a lot of waste in some cases, but again, we might at the end be able to finish a little bit faster. The cost associated with completing the activity within the crash duration is called the crash cost, which is higher than the normal cost. So normal duration is longer than crash duration, but crash cost is higher than normal cost. So if shortening or compressing the original duration or normal duration is necessary, it should be expected that the direct cost of the activity is going to increase. The formalized method to handle this problem, which is called network compression or project acceleration, is also called the time cost trade-off or relationship between time and cost. So the basic objective of network compression is to reduce the estimated project duration by reducing those critical activities in the network, which will result in the lowest added cost to the project. Again, remember, only the critical activities should be considered for compression, because the non-critical activities, until they become critical, have no effect on the total duration of the project. So some of the assumptions that we're going to make is, one of the assumptions is that the original activity durations represent a method for performing the associated work at a low cost to the contractor. Not necessarily the lowest cost, but a low cost to the contractor. Reduction of an activity's duration will require the expenditure of different or additional resources and will normally result in higher cost. That's the premise that we're going to be working under. So now we need to learn about what are different types of costs and different classifications of these costs. So project costs can be classified according to different criteria. One of them is whether they are direct or indirect costs, and this is something that you should have learned in an estimating class, for example, but we're going to talk about it again just to make sure that you do understand this point. The second way of classifying costs is based on their behavior and relationship with time. So according to the first classification, the cost can be either direct or indirect. A direct cost or direct costs are the costs directly related to the items of the project, which means they are represented by a pay item in the bid. Another definition is that these are the costs the contractor leaves behind on his or her way out in an intentional way. So if the contractor leaves a piece of equipment, it becomes intentionally, that becomes part of the direct cost. The cost of labor that built the project is a direct cost. The cost of material that were included in the construction of the project is direct cost. Equipment, production of the equipment is direct cost. So we have labor, material, and equipment costs. These are, in general, direct costs. The second type is indirect costs, which are costs necessary for the completion of the project. You cannot finish the project without spending this cost, but at the same time, not necessarily direct to any particular activity thereof within the project. Examples include, in general, supervision costs, temporary fences and access roads, which are not part of the permanent project, site and office overheads, supervision, including the salary of the project manager, who does nothing but supervising the project, but you cannot allocate, in most of the cases at least, you cannot allocate that whole salary to one particular activity or set of activities in the project. Therefore, it's going to be distributed among all the activities in what we call overhead, and that's part of the indirect costs. The other way of looking at cost is their behavior with time. How is that cost spent over time? So here we have the first type, which is called once-only cost, which is spent only once in the lifetime of the project, either at the beginning or at the end. And examples for this cost include mobilization and demobilization. Mobilization at the very beginning, surveying, temporary fence, temporary access roads, installation of permanent equipment, trailer for the general contractor, and so on and so forth. And demobilization, dismantling of equipment, removal of the trailer, moving out of the site. All of this is going to be done at the end, and that's another once-only cost. It should be noted that most of these costs which are the ones only, are indirect costs. However, some of them could be direct, like the erection and dismantling of production equipment, a tower crane, for example. But in general, most of these costs are going to be indirect costs. The second type is what we call the time-related costs. And time-related costs, as you can see in the graph here, they behave mostly in a linear way with time. So the more time, the more that costs, and it goes in a linear way. So we have a cost per unit of time that's constant, that keeps accruing as time passes. It means that costs are directly proportional to time, usually linearly, increasing with time. And examples of this time include cost of rented equipment, some types of labor costs like indirect labor, cleaning, for example, a security guard, something like that, a secretary on site, and including site and head office overheads. In general, most of the time-related costs are indirect costs. So far we talked about once only, which is mostly indirect, and time-related, which is also mostly indirect. Then the remaining type, or the third type, is what we call the quantity proportional costs. Quantity proportional costs are costs that are directly proportional to quantity. The more quantity you do, the more costs you're going to incur. So as the quantity increases, the cost also increases. And in general, most of the cases it's going to be linear, just like this. So we have a constant cost per unit, which is the slope of this curve. However, in some cases you can also have the shape, which is related to something called the economy of scale, or you can get a discount on larger quantities. If you buy in bulk, the unit price is going to decrease as the quantities increase, and that's reflected by this parabola. So examples of this type of costs include material costs, subcontractors, because again, depending on the amount of work that the subcontractors are going to do, and equipment operation costs, like fuel, for example, or any consumables for that equipment. Power for powering that equipment is going to be quantity proportional. Most of the quantity proportional costs are direct costs. So if the other two types were indirect, this type is predominantly direct cost. Another representation of the direct cost now, since we cannot notice now for a second here that in the once only cost, the axes were time and cost. In the time related cost, it was time and cost. So these can be added together. But in the third type, which is quantity proportional, we have quantity and cost. Therefore, it cannot be added to the other two. So what if we want to get a graphical representation of the total cost of the project? How can we do that? We need to convert this quantity proportional cost from quantity and cost to something related to time and cost. And this can be done through this example. We're going to look at the normal duration under normal conditions. It's going to take us that amount of time and that cost, the normal cost, to finish the activity. However, if I want to reduce the duration, I'm going to need more resources for the same quantity of work achieved. So it's going to be a higher cost for shorter time. Therefore, here we have on one extreme the normal duration, on the other extreme the crash duration and the cost associated with it, which is the crash cost. Therefore, that's going to give us something like an approximate straight line of slope, which we call the activity cost slope, which is delta cost the difference in cost, which is crash cost minus normal cost, divided by delta time, the difference in time, which is normal duration minus crash duration. That would give us the activity cost loop. So now that we have managed to combine all three different types of costs, time related, once only, and quantity proportional, we converted into a time cost relationship. Now we can add all of these three costs together to get what's called the activity utility curve, which is something that looks like this. Now this activity utility curve shows us that at a certain point in time we're going to have the lowest cost. That cost might increase if time exceeds a certain amount, and if we try to shorten the project too much, that cost is going to go much higher as well. We're going to revisit that curve a little bit later again. So with the activity utility curve, direct cost for each method of accomplishing an activity is plotted against the duration required to do it in that way. In practice, there are normally only a limited number of ways investigated, and thus only a finite number of points are defined. So here it shows the discrete points, point 1, point 2, point 3, point 4, and the cost associated with each one of these. Here's another activity with another example. So cost in the activity utility curve refers to the direct cost only, including labor, material, equipment, subcontractor, and other incidental direct costs. It can take considerable effort to develop multiple point curves for all activities. Therefore, only important activities may be evaluated, the ones that have a large impact on the cost, and you can reach such activities through what's called the Pareto analysis, which is based on the statistical assumption that 20% of the activities in the project are going to cost 80% of the total cost of the project. There's another discussion where we can find out which activities are these 20% that form the 80% of the cost. It's assumed that an activity's duration can be shortened one day at a time from point to point on this curve. These are the incremental changes. This may not be true, however, but usually does not pose serious problems in the final solution. We can accept this assumption for the time being. So by compiling the different utility curves for different activities, critical activities primarily, and even non-critical activities at this point, a utility curve can be developed for the whole project. The direct cost curve is developed by starting with the normal project duration and its associated sum of direct activity costs for their normal times, and then we can add the indirect costs, and the total cost is the sum of direct and indirect costs. The indirect cost is going to include, as we discussed before, the project overhead, including project staff, office trailer, cars and trucks assigned to the project team, office equipment, temporary utilities, and other indirect project-related expenses. And it's also going to include the general overheads, or the head office overheads, rent, lease, etc., main office personnel, main office equipment, services, and other main office expenses, and a contingency fee just for risk management. So now when we add the indirect cost here, which is usually time related, to the direct cost, we're going to get this curve, which is the total cost. And this is called a catenary curve. Catenary curve, which shows at one extreme it's high, at the other extreme it's also high, and somewhere in between is going to hit its lowest point. So for example, if we have an earth moving project with a productivity of 160 cubic yards per hour, the total work is 16,000 cubic yards. Estimate equipment operating cost except for operator is $54 an hour. Operator wages and benefits $32 an hour, normal. Overtime wage and benefits $48 an hour, and indirect cost $100 a day. We can now, based on this information, look at different production rates and draw the different discrete points that are going to be connected together to give us that utility curve. So now getting to network compression. How can we apply all of these principles to actually compress a project? Let's start talking about what are the conditions for an activity to be even considered as a candidate for compression. And we're going to find out that we have basically 4 conditions. Remember these conditions, that's extremely important. So the objective is to shorten the total project duration by compressing the duration of activities on the critical path. So first of all, it has to be a critical activity. So remember the 4 conditions before you start compressing, and for any activity to be considered for compression, it has to be first critical, as compressing a non-critical activity only adds to the project cost without affecting its time or duration. Second is it has to be compressible. Remember when we talked about delta time, which is the difference between the normal duration and the crash duration. What if an activity cannot be compressed, does not have any delta time? In this case, it's called incompressible activity. Therefore, it's going to be excluded from our calculations. So we will focus only on the activities that have a positive delta time, which is a positive difference between the normal duration and the crash duration. Third, it has to be an effective activity, and this is very interesting. Not every activity, even if it were critical and compressible, not every critical compressible activity is going to be effective. Thinking about that, if I have 2 activities, 2 critical activities connected with a start-to-start relationship, critical connected through start-to-start, if I compress the predecessor, is it going to affect the start of the successor? The answer is no, because when you compress from the end of the activity. But since the second activity, the successor, is connected to the start of the predecessor, compressing from the end of the first activity does not achieve any purpose, therefore it would make it ineffective. So, if 2 activities are connected by a start-to-start relationship, the predecessor, or the first one of these 2, is ineffective in compressing the project duration. Similarly, if we have 2 activities connected by a finish-to-finish relationship, again, 2 critical activities connected by finish-to-finish relationship, that would render the successor, or the latter one, ineffective. Because, again, as we mentioned, you compress it from the end. If you compress it from the end, still, what's driving the completion of that activity, or the duration, or the date for that activity, is its predecessor because of the finish-to-finish relationship. Therefore, if 2 critical activities are connected by finish-to-finish relationship, the latter one, or the successor, becomes ineffective. Remember these 2 simple rules. Okay, now for all the critical, compressible, and effective activities, which one are we going to start with? We are going to start with the one with the lowest cost slope. Remember again, the cost slope is delta C over delta T, difference in cost divided by difference in time for that particular activity. Therefore, we're going to look at which activity is going to cost us the least amount of money to compress by 1 day. So the basic procedure is we're going to start with the critical activity having the flattest cost slope, cheapest unit cost, and then considering successively those having steeper cost slopes. So once we compress the critical, compressible, effective with the lowest cost slope and we're done with it, we move along that continuum to the ones who have higher cost slopes until we reach the most expensive, if we still need to keep compressing. If non-critical activities lose their float time and become critical, because once we start compressing, the non-critical activities are going to lose some of their float. So what if an activity had only 1 day of float before compression? After compression, it became critical. Now we have created a new critical path, or new critical activities that have to become candidates, and the 4 same rules have to apply to these activities in selecting them for compression. The safest method, compress the network 1 day at a time to make sure that you do not create any new critical paths without noticing it, unless the minimum total float on the non-critical activities is greater than 1 day. So if, for example, minimum total float in the network is 6 days, if I compress this network by 5 days in one step, it will not create a new critical path because the minimum total float is 6 days. At each stage of network compression calculations, follow these steps. First, identify all the activities on the critical path or paths, because we might have more than one critical path. Delete from consideration those zero potential for compression. So if it has delta T equals 0, would make it incompressible, therefore it cannot be compressed. Number 3, among the critical activities, exclude the non-effective ones, as we have discussed, predecessors in start to start and successors in finish to finish. And number 4, select the activity or group of activities here, if parallel paths exists, with the lowest combined cost slope, cheapest to compress. And finally, with each cycle of compression or each step of compression, watch for the creation of a new critical path, therefore compress by 1 day at a time, except if the total float for non-critical activities is greater than 1. At each stage of network compression calculations, follow these steps. Compress the activity, update the network time calculations and the corresponding project direct cost. Repeat the steps that we talked about 1 through 7 until further reduction in the total project duration is no longer possible. We have exhausted all the compressibility in the critical activities, or until the desired project duration is reached. If I want only to compress the project by a certain number of days, I don't need to keep going beyond that, or until the cost of compression is no longer economically feasible or meaningful. For example, when I compress the duration of an activity, its direct cost is going to increase, but at the same time its indirect cost is going to decrease. So I'm going to look at this balance. Am I saving money while compressing, or am I spending more money while compressing? We're going to see an example on that. So here's the example. It shows us a network with the IPAs, immediate preceding activities, and with each activity having two durations, a normal duration and a crash duration, and a normal cost and a crash cost. Notice, for example, that activity A has a normal duration of 5, crash duration of 4, therefore its compressibility or delta T is equal to 1. It has a normal cost of 500, a crash cost of 600, therefore its delta C is 600 minus 500. So by looking at these 4 numbers, the cost slope for activity A becomes 600 minus 500, which is 100, divided by 5 minus 4, which is 1. So its cost slope is $100 per day. Now the indirect costs are 120 per day. So if I were to compress activity A by 1 day, I'm going to spend an extra $100, but at the same time I'm going to save $120 in a reduction of the indirect cost. Now we're going to pause here and we're going to have another session talking about the example, solving the whole example from beginning to end. Remember, the compression problem is not a hard problem at all. It's just a long problem because we have to repeat the calculations of forward pass and backward pass several times. Therefore, if you're going to do it manually, I highly recommend that you use a set of colored pencils and do each cycle in a different color so that you do not get confused with the numbers. Thank you, and I'll see you in the next session talking about this example in network compression.